Hi guys. Sorry that I'm kind of sick right now, but I'm going to make this video anyway. So, today's agenda, we're going to be talking about the dot product. Wait a sec. Dot product. Okay. And we're going to be talking about this thing called projection. You'll know later. Okay, so dot product and projection. Okay, so we have a vector. You know what vectors are. They have a magnitude and direction, right? What can we do with vectors? Vectors. What can we do with vectors? We can add, of course. What else? We can subtract. Sorry. What else can we do? We can divide, we can multiply. But what do vectors have to do with angles? This is our main topic that we want. Angles and vectors. What's the relationship between angles and vectors? Okay. So this is where I'm going to start. Angles. So what is the criteria for two lines to be perpendicular? Perpendicular. Well, if two lines are perpendicular, then what is the angle between them? Of course, it's going to be a 90-degree angle, right? Or we could write pi over 2 in radians. And I'm going to stick to this pi because it's a more professional way of writing it. In higher levels of math, we don't really stick with degrees that much. So what else? Let's say I drew you a set of, let me draw that a little better. Let's say I drew you a set of perpendicular lines on the xy axis. Okay, so we have something like this, and then something like this perpendicular to it. Right, there's a right angle right here. So what is true about their slopes? So let's say this line is x. Let's say this vector is x, and this vector is y. What is true about the slopes of these two vectors in order to be perpendicular? Well, they have to be negative reciprocals. They're slopes. The slopes have to be negative reciprocals of one another, right? Reciprocals of one another. And this is very important. Let's say x had a slope, so xm, I'm going to do sub m means slope. So xm, let's say it's equal to 2. So that means if y is perpendicular, then the slope of y would have to be negative 1/2, right? Because it has to be negative, so negative 2, and then the reciprocal, so we do 1 over that number. So 2 and negative 1/2. You probably know this, and you're asking me, why is this important? Well, this is very important, actually. And I'll tell you why. Let me draw a better diagram, a bigger one. Right here. Okay. This is x. This is y. Okay, I have a line here. I'm going to call it x. And I have a line here, perpendicular to it. I'm going to call it y. So let's say I drop a perpendicular line to the x, so it makes a right angle, and a perpendicular line here, so it makes a right angle. And let's call over here this in the x direction, let's call this x1, and let's call in the y direction x2. Over here, similarly, we're going to call this y1, and we're going to call this y2. So what can we say the relationship between x1, x2, y2, y1 is? Well, we just figured out they're negative reciprocals of each other. So x2 over x1, this is the slopes of this is the rise over run, right? So what's the negative reciprocal of this? So instead of y2, we put the reciprocal, which is y1, over y2, but it's going to be negative reciprocal. So it's going to be negative y1 over y2. So this is our main formula we're going to base off. And this makes perfect sense, right? Because the rise, oops, didn't mean for that to happen. The rise over runs of the two different lines should be perpendicular to each other, because the way you find slope is you do rise over run, right? So x1 is the run, x2 is the rise, y1 is the run, and y2 is the rise. So x2 over x1 equals negative y1 over y2. And a geometrical interpretation of this is we can do it using a proof. We know that since these triangles are similar, you can prove it's similar easily because all their angles correspond to each other. So for example, this angle is going to be, okay, let's say this angle over here is going to be alpha, just let's say anything. So alpha, and of course you know that this is a right angle, and so this is going to be pi over 2, which is 90 degrees, minus alpha, right? Since it's 90 degrees, you sum them all up equal to 180, and you get pi over 2 minus alpha. So this angle is pi over 2 minus alpha. This angle over here is alpha. So now we sum all the angles in the left triangle. We get, this is 90, so it's pi over 2. So pi over 2 plus pi over 2 minus alpha. So that means this angle over here has to be alpha to cancel out this alpha. And similarly over here, this angle has to be pi over 2 minus alpha. It's just a simple proof. So now you see pi over 2 minus alpha on this one, pi over 2 minus alpha on this one. We have an alpha over here, alpha over here. So these triangles are similar by angle, angle, angle. So if they're similar, their corresponding sides are equal. So what's opposite this pi over 2 minus alpha? It's x1. Remember, this is x1. So we have x1 here. What's opposite the pi over 2 here minus alpha? It's y2. So x1 and y2. And for the negative sign, we have because y1 is in the negative x direction, right? It's left of the 0. So that's just a little geometric proof to prove this thing. Okay, so let me make a new page real quick. Oops. What's happening? Okay, perfect. So we have that x over 2. Okay, so we proved by geometry and by reasoning that x over 2 over x1, I mean not x over 2, x2 over x1 is equal to negative y1 over y2. Just the negative reciprocals, right? So let's multiply this out. What do we get? We get x2 y2 equals negative x1 y1, and then I'm just gonna put everything on the other side. So x1 y1 plus x2 y2 equals 0. And this is very important. Why is this important? Well, it's important because this is a consequence. So this is a consequence of two perpendicular lines that their components, x1 and y1, were the rise and the run. Remember, their components, if you sum them up, if you multiply their corresponding components and you sum them up, is going to be equal to 0. Okay, and we have a very nice name for this. So let's consider two vectors. So this is very important. I'm going to start. So let's consider two vectors. Consider two vectors, x and y. And this means, I'm just going to write it. This means part of, this little epsilon means part of, and this means xy plane, or two-dimensional plane. If I had something like this, R3, this would mean the three-dimensional plane. But R2 just means two-dimensional plane. So this reads, two vectors, x and y, that are part of the two-dimensional plane. Okay? So let's consider that. And now let's consider, I'm going to introduce this term, it's called a dot product. So x dot y is equal to, I'm going to tell you this dot product is equal to x1 y1 plus x2 y2. This is a definition of the dot product, okay? So definition. And now you know why this thing is important. We actually have a name for it. So we know that when x is perpendicular to y, let me draw that better. When x is perpendicular to y, then indeed x dot y is 0. Right? Because if they're perpendicular, we get this result that x1, y1 plus x2, y2 is 0. But now I just said that the dot product is x1, y1 plus x2, y2. So if they're perpendicular, the dot product is equal to 0. And that's a very important formula. If two things are perpendicular, then their dot product is equal to 0. Okay? But this is only in the two dimensions. This is only in the xy plane. What if we had an xy? So let's consider an xy that's part of any dimension. So to denote any dimension, we have this r, and then we do n to denote the nth dimension. So nth dimension. So this is in any dimension. N could be 30, n could be 121, n could be any dimension you want. So this is the most general case. We have an x and a y that's part of the nth dimension. The dot product between x and y is going to be always the sum of their components. So x1, y1 plus x2, y2. But since we have n dimensions, this keeps going on forever until we get to the nth dimension. So xn, yn. And let's say n was like 20th dimension. It will be until x20, y20. That's a 20th component of the vector. Okay? So we got that under control. And let's go over some algebraic properties. Okay, so we got this. If two vectors are perpendicular to each other, the dot product is 0. Okay? And then we made a generalized case in the nth dimension. Okay, perfect. Now, let's continue. Sorry. Let's do some algebraic properties of the dot product. Algebraic properties. Okay. So we have, of course, our usual properties, commutative property, x dot y is equal to y dot x, commutative. What else do we have? Well, what goes with commutative? Distributive property. We have x dot y plus z. This is going to be equal to, we distribute it, x dot y plus x dot z. And this is the distributive. Okay? So how can we prove this? How can we prove this distributive property? Well, let's do it. Let's say we have x. Actually, this should be vector here. Let's say we have x, y, z in 2 dimensions. Then, okay, we have. So the dot product says that we take the components, right? So x dot y plus z is going to be equal to x1 times y1 plus z1 plus x2 times y2 plus z2. And since it's only 2 dimensions, we're not going any further, right? So now let's multiply this out. We get x1 y1 plus x1 z1 plus x2 y2 plus x2 z2. And I'm just going to rearrange this real quick as x1 y1 plus x2 y2 plus x1 z1 plus x2 z2. And x1 y1 plus x2 y2 is just x dot y. And x1 z1 plus x2 z2 is just x dot z. So we have just proved this right here, the distributive property. Okay? So what else do we got? Let's say we have some scalar c, some scalar c that is part of the real numbers. So it can be any real number. Oh yeah, if I don't write any number on top, that means it's real numbers. So say we have some scalar c that's part of the real numbers, then cx dot y. So let's say we have some scalar times x, and then we're going to dot this with y. Well, it turns out we can pull out the scalar, like we pull it out of an integral. So it's going to be c times x dot y. Or if we have x dot some scalar times y, then we could do the same thing. We could pull it out. It's just going to be c times x dot y. Okay? And you can prove this for yourself using the same method. So you can prove it easily. Whoops. You can prove it yourself. And I suggest you do so if you want. And lastly, our last property, let's say we have x dot x. Let's say we're dotting a vector with itself. What is it going to be? Well, the dot product says we multiply its components. So we have x1 plus x2 all the way to xn. And what's x1? Is just x1 squared. So we have x1 squared plus x2 squared plus dot 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 xn squared. And this is just equal to the what's it called? The modulus. We give a name in math. We say the modulus of something or the magnitude of something is we denote it like this. Put 2 bars, or you can put 1 bar, but I prefer 2 because I don't want to mix it with this thing. I don't want to mix it with absolute value. So I'm just going to put 2. So we denote this by the magnitude of x squared. Since we're summing, the magnitude of something is when you sum up all its, you square everything and then you take the root of that. But here we're squaring it, so we're just summing. Because you know, the magnitude of x is you do x1 squared plus x2 squared plus dot dot dot, and you take the square root of that, right? You probably did that in physics somewhere. But the magnitude of x squared, when you take the square of a square root, it cancels out. So you just have x1 squared plus x2 squared plus dot dot dot. And that's exactly what we have here. So this is the magnitude of x squared. And that's pretty important. The dot product of x with itself is just the magnitude of x squared. Okay? And we're going to be using these properties when we start talking about power. Let me just zoom in. Why is it not zooming in? There we go. Alright, let's continue. So those are some those are some algebraic properties, and now let's go to some geometric properties. So geometry. Okay. So let's say we have a x and y that's part of the xy plane, or the 2 dimensions. So we're going to draw our x1 plane, xy plane, and let's say we have a vector x and we have a vector y. So x and y. How do we add these 2 vectors? Well, we all know how to add 2 vectors. We take this little y, we move it over here, and then we move it over here. We take the tail of y, we move it to the head of x, and then the resultant is just from the tail of x to the head of y. So this is going to be x plus y. Sure you all know this. So this is going to be x plus y. We have x, y, x plus y. Perfect. What if we want to find the magnitude of x plus y? How are we going to do that? Well, as I said before, remember our formulas are going to kick in right now. The magnitude of x plus y is just x plus y dotted with itself. Remember, x dot x was the same as the magnitude of x squared. Not dot. Okay, so x plus y dotted with itself. So x plus y dot x plus y. So let's distribute it. Let's use our distributive property to distribute it. So what do we have? First one, we have a x squared. So it's the magnitude of x squared. We have a xy, x dot y. We have a plus y dot x. So we have a plus y dot x. And then lastly, we have a plus magnitude of y squared. And remember before that, when we were talking about the algebraic properties, we said that it's commutative. So x dot y is the same thing as y dot x. So this just becomes 2. So we have x magnitude of x squared plus 2x dot y plus, lastly, magnitude of y squared. Okay? So let's go back to the case where x and y are perpendicular. If x and y, x is perpendicular to y, then we know that their dot product is 0, remember from before. So then x plus y, the magnitude of x plus y, reduces to, since this thing is 0, it reduces to just x squared plus y squared, right? Since the dot product is 0. So now, I'm going to introduce some language, some notation. And this is used a lot in physics, particularly quantum mechanics. So let's say we have x and y that are part of the nth dimension. So they're in Rn. We say that x and y are what is called orthogonal. So orthogonal is just another fancy way of saying perpendicular. So x and y are orthogonal or perpendicular if x dot y is 0. So this is another definition. If x and y are perpendicular or orthogonal, so orthogonal is equal to perpendicular. Same thing. It's just a fancier word, okay? So let's continue. Why does this always happen? How do I zoom in? There we go. So annoying. Okay. So this is good. We have orthogonality, and we know how to take the magnitude of something now. So let's continue. We know, so we want to find a geometric, so basically this whole talk was about vectors in relation to angles, right? That's where we got x dot y from, is equal to x1 y1 plus x2 y2 plus dot 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 xn yn, right? That's where we got this dot product from perpendicular lines, which is a geometric property. But let's say we want to find another geometric property of dot products that has something to do with an angle. So consider this. So consider we have our xy. Again, we're part of the plane. So let me draw a couple axes. And usually we work with the plane or three dimensionals. In 3D. This is 3D, this is the z-axis, and this is our x and y. Imagine this thing is coming out of the board, or the whatever it is. So we usually work in 2D and 3D, and then we generalize it to Rn. So let's have our x and y. Let's consider y is now on the x-axis. Technically, I should draw this in a different color. 1 second, let me get a better color. So this is our y. This is y. And what should I make x as? Let's go with pink. Okay, perfect. So we have y here, and we have x here. Oh, that's a nice color actually. And we have an angle between them. What color we're gonna make that? We are gonna make this blue. So the angle between them is theta. Oh wow, such nice colors. So we have theta. Perfect. So now, let me color code everything. Okay. What if I wanted to split up x into its components? And what I mean this is, I want to construct an x that is perpendicular to y, so x perpendicular, and I want to construct an x that is parallel to y, so x parallel. And I'm going to claim that x can be constructed this way, and x is going to be equal to x perpendicular plus x parallel. Technically it should be the other way around, but it doesn't matter. So I'm saying that we can split up x into x parallel and x perpendicular. Okay? And this is all based on the assumption that y does not equal 0. So y does not equal 0 is very important here, as you'll see in a second. So y doesn't equal 0. Okay, we have this. So we dropped x parallel and x perpendicular, and of course this is a right angle. We have our theta here. We have our theta here. Okay, and what can we deduce from this? So we know that, let me get my white back, my white color. Okay, so since x and y are on the same line and they're just two vectors, right? We know that x parallel is just going to be some scalar multiple of y. For some scalar c part of the real numbers. We know that. And why do we know that? Because let's consider this. We have our y here, and then we have our x, right? This is the same exact thing, x parallel. Let's say y's magnitude is let's say 2. X is on the same line as y, so x's magnitude is going to be, let's say, 4 because it's longer. The magnitude of it is just the length. So you can see that x is 2y, right? Because its magnitude is twice of it. So same thing is here, but it's for any arbitrary magnitude, so we just say c for any arbitrary magnitude. Okay, so we established that idea. X parallel is just going to be some scalar multiple of y. C can be 2, it can be 3. In this case it was 2, but this was c, remember? So this is c, but it can be anything. It depends on x, it depends on the y. But the main thing to note is that it's some scalar multiple of y, because it's on the same plane. I mean, not on the same plane, on the same line. So you can see it's some scalar multiple of y. Okay, we got that concept. And another concept to notice, not another concept, but another key idea to notice is that x perpendicular, that y is 0. Since they're perpendicular, the dot product is going to be 0, which means that x perpendicular and y are orthogonal to each other. So we got those down. This is 1, this is 2. So I'm just going to make a new page real quick. Hopefully, perfect. So what do we got here? Let me just rewrite it real quick. We have x parallel is equal to some scalar multiple of y, and we have x perpendicular dot y is 0. Okay, and then this is all based on the assumption that I said x can be broken down into x perpendicular plus x parallel. You're just breaking it up into its components, right? So now, what if I wanted to find, let me do this in a nice color. What if I wanted to find x dot y? What would I do? Well, what's x? X, I said, is this thing, so we plug it in. So this will be x perpendicular plus x parallel dot y. And remember our distributive property of vectors, we're going to distribute it. It's going to be x perpendicular dot y plus x parallel dot y. And I think we proved this actually. Yeah, we did. So let me change colors real quick. Okay. What's x perpendicular dot y? Well, look here. They're perpendicular, they're orthogonal, so that means their dot product is 0. Amazing. What's x parallel dot y? Well, let's rewrite x parallel as cy. So it's going to be cy dot y. And remember before, I said that if you have a scalar, you can pull it out. Remember from our scalar multiplication law of vectors. So we can pull it out, so this should become c times y dot y. And so, what does this become? This just becomes c times the magnitude of y squared. Okay, so at the end of a proof, we usually write this little box over here, and then we do like this. Or we can write QED, it's a Latin word, signalizing the end of a proof. Why is my dog barking? Whatever, it's fine. So this is an important result. What does it mean though? What does this result mean for us? X dot y is equal to, well, let's go down, down, down right here. C times y squared, magnitude of y squared. So this means, therefore, if you put 3 dots here, it means, therefore, c is equal to x dot y over the magnitude of y squared. And this is important. Why? Because now let's notice x parallel. Okay? We said that x parallel was some scalar c times y, right? And what's c? We're going to plug it back in. So c was x dot y over magnitude of y squared times this y over here. Right? The y carries over and the c carries over. So this is x parallel, and this is a very important result. I'm actually going to box this. This is known as the projection of x onto y. Okay, so this is the projection of x onto y, this formula, and we write it like this. So we write proj, and then sub y on x. So this means mathematically the projection of x on y. So as I just said right now, we say that the projection of x on y, and this is equal to x dot y over magnitude of y squared times y. No, not dot y, just times y. Okay, so this is very important. We call this the projection of x on y. And to show its importance, I'm actually going to do an example real quick. So let's pick another vibrant color. Perfect. So let's do an example. Okay. My dog doesn't stop barking. Oh my god. Alright, let's do an example. So let's take an example real quick. I took care of the dog. So let's say that x is gonna be what can it be? So 1 to negative 1 1, and y is going to be, let's say, just 1 1 1 1. And of course, since it's 4 of them, we say xy is part of the fourth dimension. Oh, I haven't explained this notation for vectors. So let me explain this real quick. So this notation is a very common notation that we use for vectors. And it means that we say that this is the x component, this is the y component, this is the z component, and this is whatever component in the fourth dimension. So fourth dimension. Or we can say it as x1, x2, x3, x4. So these columns just mean that it's components, right? So if we have this 4 components, that means we're working in 4 dimensions. Okay, so we're working in 4 dimensions here, and then let's say I wanted to ask you, okay, so we have x is 1 2 negative 1 1, and we have y is equal to 1 1 1 1, and let's say I wanted to ask you what is the projection of x on y. So the projection is going to be x dot y. What's x dot y? Well, we just multiply the components. So we have x1 y1 plus x2 y2 plus x3 y3 plus x4 y4. That's a lot to write. Over the magnitude of y squared. So that's just x1 squared. No, not x1 squared. It's the magnitude of y squared. So it's just y1 squared plus y2 squared plus y3 squared plus y4 squared. That's just the magnitude of something. And then times this y over here. So times 1, 1, 1, 1. Okay? So what's the dot product of x and y? So x1, y1 is 1 plus 2 minus 1. So this is 1 plus 2. Because we're multiplying the components. So we're multiplying 1 times 1, 2 times 1, negative 1 times 1, and lastly 1 times 1. So 1 times 1 is 1, 2 times 1 is 1, negative 1 times 1 is negative 1, and 1 times 1 is 1. So 1 plus 2 minus 1 plus 1, that's 3. And then we're going to make this over, what's the magnitude of y squared? Is just 1 squared plus 2 squared plus 3 squared plus 4 squared is just radical 4 times 1, 1, 1, 1. So this is going to be equal to 3 halves times 1, 1, 1, 1. And this is going to be the projection of x on y. So that's just a neat example of how it works using the fourth dimension. So let's continue. Now, let me go back to my lecture notes. Sorry. Okay. So what do we got now? We covered this projection of x and y. Okay. So now, what do we do with this? Well, we can have some good consequences from this. Right. So let's say, let's consider again. Let me do this on a fresh page. Whatever. So let's consider again. We have an x and a y that is part of the plane. So let's draw something real quick. This is x1, this is x2. So we have x, we have y. No, we don't have that. We do not have that. We're gonna treat y on the line again. So we have y, and we have x, and we have theta. This is where the theta comes in. So let's say I want to take the cosine of theta. What do I get? Well, the cosine of theta in comparison to this x. So we know that over here we're gonna have a x parallel, and we know we're gonna have a x perpendicular right here. So what's gonna be cosine theta? So cosine theta, so it's ka. So katoa. So ka adjacent is gonna be x parallel over, and then hypotenuse is just going to be x. And when we're taking the cosine of something in comparison to its vectors, we want is going to be the length. So the length of x parallel over the length of just x. So what's the length of x parallel? Well, let's go back. What's x parallel? X parallel is the projection of x on y. So it's going to be x dot y over y squared times y. But notice this very big idea, that this is just the same thing as saying x dot y over y, the magnitude of y, times y over magnitude of y. Right? It's the same thing. Because you see, this thing just becomes y squared. But y, the vector y over the magnitude of itself, this is called a unit vector. And usually in physics, we name it y hat. So y hat is defined to be, if you put 3 equals, is defined to be equal to the vector y over its magnitude. So that's a definition of a unit vector. Okay? So when you're finding the length of x parallel, we don't count its unit vector. We only count its this thing that's left over. We don't count its unit vector. Like if you're finding, let's say, we have a vector gamma is equal to 5 I hat. When we're finding the length of gamma, so length of gamma, we just take the 5. We don't keep the I hat, right? So here we're not keeping this y hat. We're just keeping this x dot y over magnitude of y. So x dot y over magnitude of y. So that's the length. That's the length of this. And now we're dividing this all over by the length of x. And the length of x is just the magnitude of x squared, right? So let's simplify this a bit. We get x dot y over x squared. X squared y. Okay, let's keep going. No, this is not x squared. What am I writing? Oh man, this is not right. How can the length of x be x squared? It's just x. It's just the magnitude of x. The length of x is just the magnitude of x. You're probably wondering to yourself, what am I doing? Okay, so let's simplify this now. So it's x dot y over, since y is over here, we can bring it down. So just magnitude of x, magnitude of y. And this is very important, because let's see what we have here. We have the cosine of theta is equal to, right here, x dot y over magnitude of x, magnitude of y. Right? So let's multiply this whole thing by x and y, and we get that x, magnitude of x, magnitude of y, times the cosine of theta is equal to x dot y. And this is the formula that you see in all your physics classes. And we have just derived it. From the length of x parallel over the length of x is the cosine of theta. And this sometimes in physics is used as the definition of dot product. You know, like mathematicians, as I've shown in this video, we use the definition of dot product as x1, y1 plus x2, y2 plus whatever else there is. But physicists use the definition of dot product as the magnitude of x, the magnitude of y, times the cosine of theta. Okay? And from this, we get a very important inequality. It's called Cauchy-Schwarz inequality. So Cauchy-Schwarz inequality. And it states that x dot y, x dot y over magnitude of x, magnitude of y, has to be less than or equal to 1. And this simplifies to, let me just make more space. This simplifies to, here we go. It simplifies to x dot y has to be less than or equal to x, y. For any x and y that are part of Rn. So this is the Cauchy-Schwarz inequality. And where do you get it? Oh no, not x dot y, absolute value of x dot y. Yes, it's very important. I'm gonna get to that right now. The absolute value of x dot y, because the cosine of theta can be, what's the highest value for cosine of theta? Well, cosine ranges from -1 to 1, so the highest value is going to be 1. But the cosine of theta can sometimes be, theta can be a negative number, and that means the dot product can be a negative number. So we just take this absolute value, so that means it has to be less than or equal to 1, which is the highest value of cosine. Right? So we get this Cauchy-Schwarz inequality, which is very important to what we're doing. Alright? So now, what else? This is the Cauchy-Schwarz inequality. And then one more thing, we have this thing called the triangle inequality. It says that sorry. It says that for any x plus y, its magnitude has to be less than or equal to x plus y. And I'm sure you could prove this, but it's just another fact. Okay? So this is the Cauchy-Schwarz inequality. This is a triangle inequality. So I think that covers everything in dot product that you need to know. We have the projections, we have the famous inequalities that we get from it, and we have the generalized case. So I think that's it. So thank you for watching, and I'll see you later.